Monday night's lecture is going to cover rotational motion, and rotational motion is pretty much looking at everything that we've already covered, which was kinematics, forces, energy, and momentum, and now applying those four concepts to a specific situation, and that's for things that are rotating. So we have a lot of material to cover, so what I'd like to cover in this lesson would be kinematics for rotational motion. Up until this point, we've been talking about translational motion. That means the motion of an object in a straight line. Even when we were talking about circular motion, we were looking at an object's velocity at one specific moment in time, which is heading in a straight line at that moment. But now we're going to switch over to talking about rotational motion, and we're going to make sure that we keep it for rigid bodies. That just means that we're looking at solid objects that do not change their shape at any moment in time. So everything that we talk about will be a solid that holds its shape. So is it really all that different? No. As I said earlier, we're going to look at the same four concepts that we've already covered. We're going to look at kinematics, dynamics, which means forces and Newton's laws, energy, and momentum. And in this pre-lecture lesson, I want to make sure I cover kinematics. So previously we talked about position in terms of x, y, or z. For us, we didn't really look at z, but motion in either one direction or two directions. Now, since we're talking about objects that are rotating, if you pick a point on this object and it starts to rotate, how are we going to describe where it's now located? Well, you could call this location 0, and now if it's at a new location, how far away is that? Well, it's going around in a circle, so we could always look at it in terms of its angle, or as we call it, theta. So instead of looking at x, y, and z, we're now going to talk about position and displacement in terms of theta. And if you remember anything about a circle, that theta, okay, right there, that theta, is actually related to the linear quantity, which is the circumference of the circle. If it's not the entire circumference, we call it the arc length, but it's actually related to that by this radius right here. So we can say that theta, which is the angular displacement, is equal to the linear displacement, the arc length, divided by radius. And that kind of works out for us in terms of units, because if we look at the arc length, again, the location around the circle, looking at circumference, that's measured in meters, and the radius is also going to be measured in meters. So that means that the meters cancels out, and what we're actually left with is a unit which isn't really a unit. It's kind of a non-unit, but we use it to describe the motion around a circle. We're actually looking at radians. So our displacement, our theta, is going to be measured in radians. Now previously we talked about velocity, and velocity was defined as the change in position over time, or the displacement over time. So v equals delta x over t. So now, because we're not looking at delta x anymore, we're looking at delta theta, okay, the displacement, the angular displacement. That means our velocity is going to be the change in position, or delta theta, over delta time. And that's going to be what we call the angular velocity. So we're going to have the Greek letter omega, which is going to symbolize angular velocity. So the units for this would be radians over a time measured in seconds. So our angular velocity is going to be measured in radians per second. Acceleration, we looked at, the definition was the change in velocity over time. So A equals delta V over T. Because we're looking at angular quantities, the angular velocity is delta omega, so we're still looking at the change in velocity over the change in time. And since we're not talking about regular acceleration, we're going to give it another symbol. So the symbol for angular acceleration is going to be the Greek letter alpha. So alpha is equal to the change in angular velocity over the change in time. And since angular velocity is measured in radians per second, that means that the angular acceleration is going to be in radians per second or radians per second squared. That will be our unit for acceleration. So as we kind of saw earlier with the displacement, with the position, all angular quantities are related to their translational quantities by the radius. We saw theta was equal to the arc length, which was the linear, divided by the radius. Or if we rearrange this, the linear quantity, the translational quantity, is equal to r times theta. So all of our linear quantities are related to all of our angular quantities by the radius. That's going to be the way that we can go from one system, meaning like the linear system, to the rotational system. So that means our linear velocity is equal to our angular velocity by the radius. So v equals r times omega. So we can think about this a little bit. Objects that are farther away from the axis of rotation are going to move faster, and we actually had a question about that on the previous exam with the salt and the pepper on the Lazy Susan. But each one of the objects, let's say we have the pepper and the salt, each one of the objects is going to move through the same angular displacement. So for both of these objects, their delta theta is the same. So what that means is that their angular velocities, which are delta theta over delta t, are going to be the same. However, their linear velocities, linear velocity is equal to r times omega. For the object that is farther away, that has the greater radius, it is going to have the greater linear velocity. And that's exactly what the question asked you on the exam. Okay, getting back to our link between linear and angular, our linear acceleration, our tangential acceleration, is equal to our angular acceleration times the radius. Now, we have to be careful with acceleration because not only do we have what we call tangential, the linear, we also have our centripetal acceleration. Again, the other name for centripetal is just radial, which is why you see that a sub r down here. So you actually have three accelerations, or possibly three accelerations. You have tangential, you have centripetal, and you have rotational. So the centripetal, the radial, is also related to the rotational. So if something's going around in a circle, it does have rotational acceleration and it does have centripetal acceleration if the velocity is changing. So this being equal to v squared over r, the centripetal being equal to v squared over r, you can make a substitution in that the angular velocity is equal to the linear velocity by a factor of r. You can make that substitution in and get omega squared times r. So here's just kind of a summary of our three quantities that we use to describe motion, our kinematic quantities, their rotational equivalents, and how they're related to each other. Again, this x equals r theta. Since we're talking about things going around in a circle, oftentimes the x is described as s. There are some other quantities that we need to remember since things are going around in a circle. We can also talk about the frequency of rotation. And we have a regular frequency, which is cycles per second, is equal to the angular frequency, which is rotations per second, by a factor of 2r. Honestly, guys, we will talk about this more with oscillations when we get to that chapter. But we did already talk about the fact that the period and the frequency are inverses of each other. The period is the time for one revolution. Since we're talking about things rotating, we can talk about things going around in a circle. And the frequency is how many times per second an object goes around in the circle. So when we first talked about kinematics, like our very first lesson or second lecture, we talked about the tools for kinematics. So we had the two definitions and we had the three equations, which were our tools for kinematic problems. Well, those tools have not changed. We still have the two definitions, which were for velocity. In this case, is angular velocity. So we still have the definitions for angular velocity and angular acceleration. And we still have the same three equations. The only thing we have to do is change them to be in terms of angular quantities. So what we see here are the three equations that we had. They just look a little bit different because I copied this from a certain place. But we have our VF equals VI plus AT. We have our delta X equals VIT plus 1/2 AT squared. And we also have our VF squared equals VI squared plus 2A delta X. So those same three equations are in play again, but instead of using V for velocity, we're now using omega for angular velocity. Instead of using X, we're now using theta. And instead of A for acceleration, we're now using alpha. But the same three equations are in play. We've just changed them to be in terms of angular quantities. So we still have the same 5 tools. That has not changed, guys. It's just that the notation, the symbols, have changed. Okay, we're going to wrap up this lesson by looking at an example problem. So we have a wheel that starts from rest and rotates with a constant angular acceleration and reaches an angular speed of 12 radians per second in 3 seconds. And we need to find two things: angular acceleration and through what angle does the wheel rotate during this time. So just like we would with our old kinematic problems, we're going to make a list of what we know and what we're trying to find. So they tell us that it starts from rest. So our initial angular velocity is 0. It tells us that it reaches an angular speed of 12 radians per second. So our final angular velocity is 12 radians per second. And it does this in 3 seconds of time. So t equals 3 seconds. And we're looking for the angular acceleration, and we're looking for the displacement. Okay, through what angle does the wheel rotate? So they're asking us displacement. Okay, so we're going to take a look at acceleration first. So I know initial velocity, final velocity, time, and I'm looking for acceleration. So if I think about my kinematic tools, probably the best one is final equals initial velocity plus alpha times t. So we have a final equal to 12, we have an initial of 0 plus alpha times t, which is 3 seconds. So if we go ahead and do the algebra, alpha comes out to be 4 radians per second squared. So there's our first answer. The second one is looking for delta theta. So I know of two equations that have delta theta. We have the delta theta equals omega initial times time plus 1/2 alpha t squared. Or we can use the omega f squared equals omega I squared plus 2a delta theta. It's your choice, whichever one you want to use. I think I'm going to go for the squared one. So omega final squared equals omega initial squared plus 2 alpha delta theta. And if I go ahead and plug in my numbers, we have 12 squared equals 0 squared plus 2 alpha we just found is equal to 4 times delta theta. And if you go ahead and do the math, do the algebra, your answer actually comes out to be 18 radians, which is different from what I have in the PowerPoint. So let's get rid of that, and our answer is 18 radians. So that's it, guys. It's just the same kinematic problems as we've done before. All we're doing is replacing the linear quantities in the equations and the definitions with the angular quantities. Okay, we'll pick up from here in lecture. Have a good night, guys.